Good afternoon, everybody. We're the FIU Urban Research and Robotics Rescue Team. My name is Cosmo Rodriguez. This is Maximiliano Dre and Daniela Mojo. For our design, we're essentially creating a scaled-down version of a small robot that's going to be capable of delivering granular material. During a lot of disasters, both natural and unnatural, infrastructure can be destroyed. So the purpose of this is to basically get supplies and medicine to people and this little robot can basically go over rubble and various destroyed terrain. Basically, we're being graded on this criteria. We have a time constraint of about 3 minutes, so we have to traverse this course. Our robot's going to have to be capable of traveling through sand, through water, and up several flights of stairs. One of the design constraints is that we must use rechargeable batteries. And additionally, we have these dimensional constraints where our robot cannot be larger than this. For our scoring, we're essentially scored on 3 main factors: the usable payload that our robot can deliver, divided by the time it takes to reach the destination, and the energy that the robot uses up. This is our project timeline. This is what we've been completing, and this is the end of what we have on that now. For our main design, we essentially had 4 main criteria that we had to fulfill: our mobility mechanism, our stair climbing mechanism, our dispensing mechanism, and our powering wireless controls mechanisms. For our design choice for our mobility, we had 3 basically designs we can go with. We can go with a Lego design, we could have gone with tracked, or a wheel design. Because we're graded on time and energy, we ultimately decided to go with the wheel design because it gives us a higher speed and a lower energy, even if it causes our climbing ability to require more work to input. These are our alternate designs that we initially were going with. That design is actually a retractable wheel that we were brainstorming an idea of. Ultimately, we chose not to use it and just go with standard wheels. These 2 designs were also alternatives that we could have used. This one uses a small pivot point in the center, and this one actually had 6 wheels on 1 axle, and 3 on each, and it would rotate as it would move along the track. This is ultimately our final prototype. As you can see, we have 4 wheels, 2 larger ones in the front, 2 smaller ones in the back, a large climbing arm, and a large hopper in the center of our chassis. For our overall design, we essentially went through this criteria for designing our robot. We started with our arm design, and we went through this entire task of designing. However, when we got to the end, we weren't done. We would actually go back to the arm design and do another iteration of our design, because sometimes something in the middle can cause issues in the back. So and we did this about 3 times, allowing us to come to this design. For our wheel selection, we were constrained by our size. Ultimately, we decided to pick a larger wheel and a smaller wheel. The larger wheel is a heavier lawnmower wheel. We used an 8-inch diameter. The smaller wheels are 6 inches, and they're actually air-filled in order to save on weights. We ultimately chose the larger wheels for the larger wheels so that our robot can actually climb through both sand and water. For our arm design, we had to choose the shape and the size that would allow us to fulfill the task, the leg requirement, and the motor design. We had to center the arm along the chassis because when it climbs up, it doesn't create a moment and topples to the side. Additionally, it was shaped in order to get to the maximum area where it can grab. And additionally, when storing the vehicle, we can actually tuck it underneath the robot in order to save on space. For a simulation, we did several stress analysis. We estimated that each arm point would only get up to 25 newtons. We only got about up to 19.1 MPa at our maximum points. And because ABS has a very large yield strength of around 40 MPa, we were fine. We initially did strain analysis, which were actually very low, so we were good on that aspect.
So continue with our analysis. We looked at the torque required by each wheel in order to move the chassis back and forth. In order to calculate this torque, we needed to assume 3 different values. That is the top speed, the time that it would take us to accelerate to that top speed, and the total estimated weight. Now, we deemed that 26 centimeters per second was an appropriate top speed due to the total length of the track. We wanted a negligible amount of time to accelerate to this top speed, so we chose 0.8 seconds. And we estimated a total of 14 pounds for weight, which turned out to be accurate. So knowing the total diameter of the wheel and the top speed, we were to calculate the amount of RPMs that were needed, which turned out to be 20. Knowing the time that it took to accelerate to the top speed and the total weight, we were to use kinematic equations and Newton's second law in order to obtain a torque of 365 ounce-inches. Then Then we looked at whether or not this torque was enough to go up an incline, which we had to go through. And through similar analysis, we noticed that the torque to accelerate the top speed was much bigger than the torque needed to go up. So, next we looked at the analysis of the arm motor that drives the arm. Essentially, what needs to happen is this arm needs to lift the two front wheels up so that at least half the diameter is above the step. And the main design criteria that drove this were the center of gravity and the reaction forces at the wheel. Now, knowing the distribution of the weight at each of the wheels, we were able to calculate the torque needed to lift the front part of the chassis, which is 521 ounce-inch torque. We also wanted to keep in mind that we wanted to have low RPMs for the motor we chose in order to have control over the lifting mechanism. As far as our payload container, we designed a gravity-driven mass flow hopper. The reason we chose this design is because it takes advantage of the gravity that's already there, therefore no needed energy input on our part, which was convenient. The main parameters that drove the design of this hopper were the angles which the hopper made with a vertical axis, the vertical axis being parallel to that of gravity. It was studied that angles from 0 to 40 produced good mass flow rates. We took 40 degrees in order to obtain a maximum amount of volume and therefore payload to deliver. The hopper is made of styrene. We expected to have a 0.32 kilograms per second mass flow rate and a total load of 6 pounds. We need to be able to dispense the payload at a reasonable time. So we designed a dispensing mechanism comprised of a rack and pinion. As you can see on the bottom right, we just have a motor driving a pinion that moves a rack back and forth. That's attached to the outlet of the hopper. Therefore, we can dispense the payload at will. We chose an RPM of 75. Therefore, we expect the opening and closing to happen in half a second. So then we did stress analysis on the chassis. We were expecting a lot of stress due to the lifting mechanism, so we designed a housing for the motor that drives the arm. Now, knowing the transmitted loads from the arm, we went ahead and calculated the safety factors, and which proved to be more than satisfactory. As you can tell, we had two different cross sections in order to fit the motor snugly with its contours. As far as the rest of the chassis is concerned, we had two major components to look into. We went ahead and found out the transmitted loads, and we essentially solved the stress equations for the moment of inertia term, allowing us to calculate a minimum thickness at which the chassis won't yield. So this threshold was 0.25 centimeters thick. We went ahead and used 0.5 centimeters thick in order to be confident in our design. And of course, finally, we looked at the stresses on the shafts. On the steel shaft, we found out the transmitted loads, and we had safety factors that were satisfactory.
Our chassis is manufactured out of PLA plastic. Due to the size restrictions of the 3D printer, we had to print it in two separate components, as you can see in the bottom left-hand corner. We fastened these two components together using screws and an aluminum brace. Some features of our chassis are spaces for the motors and a slot for the hopper. Some standards that we used throughout the design process were the 2015 ASME Robots for Relief design rules and regulations. When it came to choosing shafts, screws, and bearings, we referenced ASTM and SAE, amongst others. Our system controls is composed of four separate components. We start with the transmitter and receiver system. The receiver being connected to the electronic speed controller, and the electronic speed controller controlling the voltage and the speed of the motors. We had 4 channels in total that we used. 2 channels for the 2 motors on the front wheels, 1 channel controlling the motor arm, and 1 channel controlling the dispensing mechanism on the bottom of the chassis. Based upon our operating conditions, we determined we needed a 9.6 volt battery. We then calculated the power based upon documented amp ratings. From there, we estimated the amount of time it would take for 1 run of each motor operation. With those estimated times, we were able to calculate the battery capacity needed. We estimated with 100 milliamp hours, we could complete 2 runs. Here's a preliminary simulation of our climbing mechanism. Here are several videos showing our testing. The first video on the left shows the mobility, or will show the mobility of the robot going 365 degrees in place. The second video shows the strength of the climbing arm. The third video shows the dispensing mechanism. The fourth video showed the robot going up an incline.
Oh, I see.
It worked before
Code unavailable.
Magic eye.
Yeah, no matter how many times we tested it, and the last video would have shown the robot going across sand. To conclude our results, our vehicle is able of turning 365 degrees turning radius. It goes up an incline plane. Its dispensing mechanism is completely functional, and it can handle multiple terrain. However, the climbing mechanism needs improvement. Based on our calculated torques needed, we selected these parameters for our torque motors, giving our wheel motor a factor of safety of 1.3 and our arm motor a factor of safety of 1.15. Our top speed and the time to open the dispensing door worked as predicted. However, the flow rate was under-predicted. However, we found that the extra time needed to dispense the full amount of payload was negligible. We initially estimated that the cost of the prototype would be $536. So we took a budget of $700 to take into account unforeseen costs. Our final prototype cost was $559. We use NiMH batteries, which do not contain harmful metals. PLA, if properly composted, can be biodegraded in 60 days, and it does not emit toxic fumes when degrading, and it's also carbon neutral. We have a compact design that is transportable between different sites. We have intuitive design features to accommodate various users, and throughout the design process we use US and SI units. In conclusion, our design was successful in its dispensing mechanism, its wireless control, its mobility, the size restrictions were met, and the arm can support and lift the chassis. Some future design considerations to push this design a little bit further. Automatic controls for the dispensing mechanism, designing the chassis for easier access, deeper treaded wheels, and improving the mounting design for the electronic components. This concludes our presentation.
Wait for questions? Okay, good. By the way, you guys did a nice job on the actual prototype building, okay, so props to you. Talk about a little bit about the shortcomings on the climbing mechanism in general.
Well, the video would have showed you quite clearly. Basically, the arm works as designed. It's essentially lifting the front part of the chassis, and so that the half of the at least half of the diameter is going up the step. But the problem is that currently the wheels aren't gripping onto the step, so it doesn't have that oomph to go onto the step. So that was the main issue, and that's what we were suggesting: deeper treads in order to have better traction to get us up there.
One thing I see from here, because it's the right angle, that the center of mass is like towards the back. And some of the simulations, you know, that you showed, if you get the hook, right, you go up like this, right, I tend to think that it's just gonna kind of fall back. And maybe that's also the issue, that it's just a center of mass issue that you have to be aware of here. That's because in the simulation it shows that, I don't know if you guys put the gravity.
Yeah, we put the gravity, but we're also trying to put a mass to it, but for some reason it wouldn't like lift down.
Really?
But like when we actually tested it, it did like obviously swing down.
Got it. Did it climb? It didn't.
Well,
Okay,
it
didn't
wouldn't
like-
lift,
okay.
it would lift, but it didn't climb.
Sorry.
This was a competition. Who are you competing against on this? Was it internal or was it?
No, it was an ASME competition.
Okay.
Other schools, most likely.
Yeah, it's, you know,
Yeah, other schools, like it's a collegiate competition.
Huh?
Yes.
It's a
Yes,
collegiate competition
Yeah.
against other schools.
correct.
Yeah. Well, when you did the 3D printing of the body, did you come across any issues while it was printing? Or did it, like the first time shot, it came out good?
First shot, it came out
Yeah.
good, but it took 17 hours to print this chassis.
It took a little time.
Yeah, because we got a 3D printer and we still got to calibrate certain things. Sometimes it does it really good, other times it will just stop dispensing the plastic and it just kind of moves around, doesn't do anything.
Oh, ours was just straightforward. This is the first one when we printed.
Okay, I was just kind of curious if you had problems with creating it.
So Renee and Michael at the Emory Lab is great at 3D printing and doing an excellent job.
So just a quick question about the dispensing mechanism. So you guys had sand, I know we didn't see the video, is it
Rice.
sand?
Rice.
Rice, okay, so
So it's a little thick.
is that, the competition, that's the main thing that
Yeah.
you're, okay, or that was what they were asking you?
And any small granular material, we
Okay.
just chose rice.
Sure,
It could
sure.
have been grains.
And so then you would drop it, there's a hole, I guess?
Yeah.
Okay, all right.
There's,
No, I guess the competition, you drop it down into a
Yeah.
hole on the top of that box?
Right, we would essentially climb these steps
Uh-huh.
and get on this step and release the payload.
Okay.
However, it was that we didn't, the idea was that we drive just right over it
Uh-huh.
and use the, gravity driven.
Right, okay, makes
Flow.
sense.
That was the main thing.
Okay, thanks.
And we had an outlet of 7.5 centimeters by 2.5 centimeters.
Okay.
What is your competition?
It was actually April 5th. It was supposed to be April 15th, but they kept changing the competition, and it was actually the weekend of Passover and Easter.
Yeah.
Yeah.
What did you guys do?
We did not.
we didn't go to that.
Any other questions?
What would you say is the most challenging part of the whole job?
I'd say prototyping, getting all the components together and making sure that they all work together.
I'd say the assembly was a little difficult too.
Yeah, assembly, definitely. Because of the size constraints, it made it very hard. If you look inside of our chassis, the motors are sitting right next to each other. So it made it a little bit difficult to make changes or, when a wire came off, to take everything out.
Gotcha. So you're constrained with the size of your plant you're working with.
Yeah, because that's basically the maximum size we can put it at.
I see.
We can't go any further.
And the rules mandate that.
Yeah, the rules
Yeah.
say it was like 30 by 25 by 20 centimeters.
Okay. Thanks.
Well, thank you.
Next we have senior design team number 15.